Okay, let's begin the morning session. So we now have William Slofstra, who will tell us about Tsirelson problem and linear system games.
So thanks very much for the opportunity to speak here, and thanks for waking up early on the last day. So I'm going to talk about essentially a math problem, the kind of thing that comes up, the really basic problem we like to ask about non-local games that we've never really been able to answer. And the kind of main message I want you to take from this talk maybe is that there's still way more questions than we can answer, and we're maybe just starting to be able to answer some of them. Also, this talk contains some joint work with Richard Cleve and Li Liu, and I should thank Anand for letting me borrow his computer. So I want to actually start with a really simple-minded question. If you're a physicist, you're probably going to find this really too simple-minded, but I think it's a good kind of, it gets us pointed in the right direction. So if you kind of talk about what is the conventional wisdom about the basic quantum mechanical building block of our physical universe, then because whatever plug-in, whatever explanation is the favor of the person you're talking to, maybe because we have always finite energy levels, everything should really be able to be described by a finite dimensional Hilbert space. On the other hand, when we're learning about quantum mechanics, we learn all these infinite dimensional models, and that includes when we go to quantum field theory, we learn things that seem to have infinite dimensional Hilbert spaces in them. So a really simple-minded question we can ask is, maybe there's something to that. Could nature be intrinsically infinite dimensional? Maybe that's our basic building block. And if you really talk to people who know what they're talking about, maybe not me, but I trust people who do, the answer is probably not. That's the wrong way to think about things. The fact that quantum field theories are infinite dimensional is really a trick of the model, and really kind of the accessible part is finite dimensional. But once our curiosity is aroused, maybe we can kind of keep going with that idea. And really the kind of thing that makes me really curious is if it was infinite dimensional, could we recognize that in an experiment? Like maybe forget what the models are saying, yes or no, but let's say it did happen to be infinite dimensional. Could we tell? And what kind of experiment would we like to do? Well, the simplest type of experiment maybe would be a Bell type experiment. So just to get ourselves kind of in the mood to think about these things, I'm going to go over what we all know really well. So I like to think about Bell experiments through the lens of non-local games. So in a non-local game, of course, we have two players. I'm only going to think about the two-player case in this talk. So Alice and Bob, and they receive inputs, X and Y, from a referee. And then they return outputs, A and B. And the referee looks at the outputs, compares them to the inputs, and decides based on the rules of the game whether Alice and Bob win or lose. The winning conditions are known to Alice and Bob in advance, and they want to cooperate to win. So what makes this difficult for them is that they can't communicate while the game is in progress. And so we can ask, what can Alice and Bob do in this game? And if we take the perspective of an outside observer, then really all we can see is what Alice and Bob output when they receive inputs X and Y. So if we imagine the game is being played over and over again, what we can write down is the probability that Alice and Bob output A and B on input X and Y. So that's kind of our fundamental description of what's going on in one of these non-local games. This correlation matrix, which is a collection of probabilities, P, A, B, for every input X and Y. So what can this correlation matrix be? Well, first of all, if we fix a finite number of questions and a finite number of answers, and that will always be the assumption in this talk, then we're just talking about a collection of numbers in R, m squared, n squared. So that's the first thing. We're just talking about finite collections of numbers. And if so if we want to then pin down what these correlation matrices can be more than that, we need to figure out what model we're going to use. So classically, we might say Alice flips a coin, receives input X, and flips a coin to decide what output she's going to choose. So for every X, she has a probability distribution on answers given by Pxa, and Bob has the same thing. So the probability, PAB, given XY, is the product of the two probabilities. And we could spiff that up a little bit. We can imagine they have shared randomness and so on. But really what I want to talk about in this talk is the quantum picture. So in the quantum world, we would say that Alice and Bob can have a shared quantum state, which belongs to some tensor product of Hilbert spaces. And they each measure that state in their laboratory. So for every X, Alice has a measurement. And so we have measurement operators, mxa, for that measurement, depending on X. And Bob has the same thing. And so the probability that they output A and B on input X and Y is this joint expectation. So that's all pretty standard. I want to call the attention to one feature we normally don't. We just write down without thinking, and that's the tensor product in the middle of this. So why do we put a tensor product there? Well, we have an axiom of quantum mechanics. So if we're describing this in physicist language, we say that Alice and Bob are in space-like separated places. Maybe their labs are in separate wings of the building, and they're going to have to do this game really fast, so they can't, there's no time for any communication to happen. And so how do we describe, we know that each one of their local systems is describable by a Hilbert space, but what's the Hilbert space of the joint system? Well, there's an axiom that says if we take a composite system out of two local systems, then we should take the tensor product. So now let's talk about Bell inequalities. So one thing I want to say, I'm going to have some diagrams in this talk, but they're all completely schematic. Most of the time they're about sets we have no idea how to draw anyway. And so don't take any of these diagrams literally. So we can write down the set of classical correlations. Let's call that correlation sub C. This would depend on a set, the number of questions and the number of answers, which I'm going to drop from the notation in the future. But always think that those are fixed in the background. And we have a set of quantum correlations, all the things that that have a quantum model. And both of these are convex subsets of R, M squared, N squared. So if we, I should say we can also talk about the value of the game. So given one of these correlation sets, we can talk about the probability that Alice and Bob wins with that correlation. And then we can define the maximum winning probabilities in the classical world and the quantum world. Those are called the classical and quantum values of the game. So for the classical one, we just take the maximum across all correlations in the classical correlation set, and we do the same thing for the quantum. And if we think about what a game does, if we look at all the correlations where we get a specific value for the winning probability, that turns into a hyperplane. So here I've drawn the lines for the classical value of the game and the quantum value of the game. And the idea is, if we knew that the classical value of the game was strictly less than the quantum value of the game, if we pick any correlation inside these two lines, let's see if the mouse pointer works. Yes, it does. Good. So we pick any correlation in this band. If we could implement that with a device, a physical device, then we would get an experiment, which allows us to show that we would then observe that we get some winning probability which is better than what we'd expect classically. So we get two things out of that, right? We get, first of all, just from the mathematical fact that the values of the games are different, we get that the correlation sets have to be different. And then we get this great fact that theoretically, if we could implement that correlation, then we could show that in an experiment, if we could implement it. Now, of course, the whole point, I mean, one of the reasons we're here, as all of you know very well, is first of all, we have Bell's theorem, which says that there are games with this property, and second of all, this has been implemented many times in experiment. And so we could kind of say, like, why does this sound like a good idea to say, well, theoretically we could do this in experiment? Well, it's really only because we've actually been able to do it before. But it doesn't mean just because we write down a correlation in the future that we'll be able to implement that correlation. OK, so let's go back to the question I asked at the beginning. Finite versus infinite dimensional, the picture should be pretty clear. We just want to do exactly the same thing. We want to write down two sets of correlations. And then we just want to see if we can separate them with a Bell experiment. So let's have a first try at this. So remember, our quantum correlations are the things that can be written in this form. And so we have our set CQ. Let's keep the notation for quantum correlations that we had before. But let's say that this one is the finite dimensional one. So what does that mean? We're going to restrict the Hilbert spaces we use to be finite dimensional. So that's our kind of basic, maybe one of the assumptions we really like to make in quantum information. We assume that finite dimensional Hilbert spaces, or we often assume that they represent everything that can happen. Note, however, we're not picking a bound on dimension. The dimensions of these things could be 100, they could be 1,000, they could be 10,000, or higher. So what do we do for infinite dimensions? Well, we need a new notation for the set, so we'll call it C sub QS. This is basically the exact same thing, but we're allowing the Hilbert spaces to be infinite dimensional. In case you're curious, the S stands for spatial tensor product. And if you don't know what that means, you probably shouldn't ask further questions. Okay, so can we separate CQ from CQS, our finite dimensional and our infinite dimensional sets, with a Bell inequality? That's kind of the question we were asking at the beginning. And the answer is no. This is completely the wrong picture, unfortunately. So what's wrong with this picture? Well, first of all, I've drawn two convex sets. That's OK. These sets actually happen to be convex. I've drawn them closed. So first of all, that's a problem. These sets aren't closed. But maybe I just fixed that by making some of the boundaries dotted. Well, the problem is the closures are the same. Okay? So this is actually a great fact, because if we think about the fact that these things aren't closed, we really should write down a third correlation set, which is the closure of the finite correlations. And the reason for that is our correlations represent kind of idealized objects anyway. We don't expect to ever be able to represent them exactly. And so if we're thinking that maybe here's something where we could build a series of devices and get in the limit this set of correlations, then why not throw in the closure? And second of all, if we did have something in the closure, we'd never be able to distinguish it from the stuff that we started with in an experiment. So really maybe we should talk about the set of correlations being the closure of the set of finite dimensional correlations. And by the same argument, we should throw in the closure of the infinite dimensional correlations. That would give us up to 4 correlation sets. So fortunately, the closures are equal. So we only get 3 correlation sets. So it's actually kind of a good thing that these closures are the same. We get one less set to consider here. But it really screws up this idea of trying to separate these sets with a Bell inequality, because the real picture is something more like this. All these sets have the same interior, and then they just fight over different portions of the boundary. So the CQ would contain the entire boundary. The A stands for approximal, by the way, so things that are approximal by finite dimensional correlations. And then maybe there's some portion of the boundary, for instance, which is in CQ, but which would mean that it would be in all the sets. Or maybe there's some portion which is in CQS, but not in CQ, and so on. So what we know is that we have this hierarchy of convex sets, CQ, finite dimensions inside of infinite dimensional QS inside of the closure. But we know nothing else about these sets, actually. So the talk, if that was the end of the story, the talk could end here, and we'd be done. But fortunately, there's more we can say here. And we can maybe catch on, if we're thinking about it. We've actually made a big assumption here, which is that the Hilbert space is the tensor product of the 2 local Hilbert spaces. And maybe this is too restrictive. So why would we think that? Well, there's another model that we could use for composite systems. And this model is sometimes called the commuting-operator model. So the idea is, rather than having 2 local Hilbert spaces, we just have one big Hilbert space. And then we say that this big Hilbert space describes a composite system if Alice and Bob each have their own algebra of observables acting on this Hilbert space, and the 2 algebras commute. So for correlations, that would mean that we have PAB equal to XY, PAB XY equal to this joint correlation, where Bob has his measurement operators, Alice has her measurement operators. But rather than taking the tensor product, we just take the ordinary product. The state psi just belongs to some big joint Hilbert space, which has no tensor product structure. And what makes this product here an actual measurement, why this is kosher to implement, is the fact that these measurement operators commute. So there's some situations where we have to use this kind of notion of composite system. If we talk about algebraic quantum field theories, for instance, really this is the notion we have to use to get for a theory to exist. If we put on the tensor product structure, it's too restrictive. OK, so what do we know about this set of commuting operator correlations? Well, we know it's closed. And if we think about what happens, maybe we've got it right up here. If we did have a tensor product structure, we could just forget about it, and we'd get a commuting operator correlation. We would replace we would have a measurement which came out as the original measurement operator on the local Hilbert space tensor the identity for Alice, and the identity tensor Bob's measurement operator now is Bob's new measurement operator. But we can forget about the tensor product structure in that way. And therefore, any one of these tensor product correlations is actually a commuting operator correlation. And since we know that this set, it turns out, is closed, we actually get that this set CQC contains our finite dimensional approximable correlations, the CQA. So we get a hierarchy of these 4 sets with our CQC coming in on the right. Now this represents an opportunity when we see something like this. We might go, well, if we really think quantum correlations are kind of a fundamental object we want to study, it's a really bad thing for there to be 4 possible sets. So what we really should do is just show that these sets are all equal. And now that we've got a new set up there, we've got a golden opportunity. Let's just show that everything in CQC is finite dimensional and tensor product. And so can we do that? Well, we first start with the idea, well, I know if H is finite dimensional. So let's say we're starting here with something that would be in this commuting operator model. But if H is finite dimensional, then what we can do is we can actually find, this is a little bit of a lie. You have to do something slightly more complicated, but this is the gist of the idea. You can actually find a way to break up the Hilbert space into a tensor product and the measurement operators into tensor product operators. And therefore, you recover a tensor product correlation. The problem is that this argument doesn't work at all if the Hilbert space is infinite dimensional. So you can just show that the algebra will not go through. They're not algebraically. So if we work on the level of kind of algebraic isomorphism, you can show that this can't happen in some situations. Now that might say, well, we know then that commuting operator correlations are a broader class of correlations. And we don't from that because we can't actually see algebraic isomorphism when we do experiments. We're not seeing that. We're just seeing the correlations. So all we know is that CQC is sitting on the right-hand side of this inequality, but it doesn't tell us it's still possible for all 4 of these sets to be equal. So we've basically run into Tsirelson's problem now. So we've got 4 correlation sets. We've got this 3 that involve the tensor product, 1 that involves commuting operator. And so we'd like to know, are any of these correlation sets the same? And in particular, are the commuting operator ones the same as any of the tensor product ones? And that one in particular is Tsirelson's problem. It's maybe a good point to tell you a little bit about where this problem originates. So in the 80s and early 90s, Tsirelson was working on these correlation sets. And maybe, at least as far as I know, the first one to really write them down and study them from this perspective. And very far-sighted work, and as he writes on his webpage, at least, not really appreciated at the time, leading him to write down a bunch of theorems that he thought he knew in a survey paper without proofs and move on to other things. And in the 2000s, in particular when Nevescas, Peronio, and Assin were writing their NPA paper, they went to this old paper of Tsirelson's and looked and said, well, we are, as I'm going to revisit, we're calculating something that involves the commuting operator correlations, but it would be really nice if we were calculating something involving tensor product correlations. But here's a theorem of Tsirelson which says that they're the same. So I should say, actually I didn't say this, so what was the theorem that he wrote down? What he wrote down was that CQS was equal to CQC. Or maybe it's a little hard to interpret. Maybe he meant that CQ is equal to CQC. It's not quite exactly clear. I think CQS. But anyway, so for NPA, this was great because if you're commuting something commuting operator, it meant you were computing the same thing for a tensor product. So they wrote to Tsirelson to ask, this is great. You shouldn't just take people's word for things. They wrote to actually ask for a proof. And it turned out he found that whatever proof he'd had didn't work. So no more theorem. So what he did is he wrote this up as a problem statement, and this became known as Tsirelson's theorem. He pointed out right away that there is more than one version of this question. So his original theorem was CQS equal to CQC. And so the question he asked was, is this theorem correct or not? But he pointed out right away that actually the one we care about the most is whether CQA is equal to CQC. So I like this terminology which I've borrowed from Vern Paulson, which is to call these different versions the strong. I call the one with CQS and CQC the middle, and the last one, whether CQA is equal to CQC, the weak version of the problem. And so the most interesting one is this weak one. And the reason for that, we'll get to in a second. Let's talk about the strong one, for instance. So really what we're comparing to, really what we're comparing here is 2 axiom systems. That's kind of the important point here. We'd like to know whether or not commuting operator correlations are more expressive than tensor product correlations, or are they the same? Okay, why do we care about weak ones the most? Because CQA is a closed convex set, and CQC is a closed convex set. So if they're different, then we can actually show that with a separating hyperplane, which means there actually has to be a game which would separate them, which means we'd actually get our original thing that we wanted, the Bell inequality that would allow us to test infinite dimensional, an infinite dimensional nature of reality. So whether or not there is a game that could separate so tensor product from commuting operator is the same as asking whether these two correlation sets are the same. And of course, the only way they can be different from what I said about what happens in finite dimensions is if the commuting operator was using infinite dimensional Hilbert spaces. Okay, so that's kind of the history of this problem. What do we know about it? Well, the most important thing we know about it is this. It's the theorem of Ozawa, but really based on work of two groups who discovered it independently. One is Tobias Fritz, and the other is Yanga, Nevesquez, Palazuelos, Perez Garcia, Schulze, and Werner. And they found that these last two sets, CQA and CQC, are the same if and only if Kahn embedding is true. And what is Kahn embedding? The main thing we need to know about is a very difficult and well-known problem in functional analysis. So this doesn't answer the problem for us, but it tells us about how hard we'd have to work to find the answer. Really, really hard. And maybe it's going to be a while while this is still mysterious. Okay, so what I want to tell you about is we can actually get an actual answer to one of these questions finally. It's not the one we'd like the most, but it does tell us something, which is that our second set and our fourth set are different. CQS is different than CQC. So we may not be able to test it in a Bell inequality. We don't know yet, but at the very least we know that commuting operator correlations are actually different than tensor product correlations. They have different expressive power. Okay. Now, I don't want to leave you with the impression that these are the only questions that matter here. Actually, we can ask about separations between the other sets we've already looked at, the tensor product sets. We've said that we can't use that to find Bell inequalities to separate the sets, but that's not the only kind of question we could ask. There's also, for instance, the resource question, right? We think about a non-local game as a computational task. And Bell's theorem is saying, well, if we have entanglement, that's a resource that allows us to do better on this computational task. So then we can ask questions about that resource. Like, for instance, if I have a given game, can I always play it optimally with finite dimensional Hilbert spaces? Or is it possible that there's a game where I can get within a tenth of the optimal value on a Hilbert space of dimension 10, and within a hundredth on a Hilbert space of dimension 100, and within a thousandth on a Hilbert space of dimension 1,000, and so on, but it never stops? We don't know the answer to that. It would happen if and only if CQ is not equal to CQA. Or in other words, we would get a finite bound on Hilbert space dimension if and only if these two correlation sets are equal. We do know some variants of games. So people have been really interested in this problem and have studied it from a number of different angles. And one thing we know is that if we change the definition of game a little bit, like maybe we allow quantum questions, just to pick one example, then finite dimensions do not suffice. So maybe the smart money is that CQ is not equal to CQA, but we don't know. Another question, and maybe it's kind of the first question we run into when we're studying non-local games, is can we compute these quantum values of the games, either in the tensor product model or in the commuting operator model? And of course, for computational complexity theorists, this is related to the power of MIP star. So I want to talk about the second question a little bit. So what do we know about computing these two values? Well, first of all, we have a process we can use, not an algorithm, but a process to compute both of them. If we want to compute the tensor product value, we know that we can always achieve the optimal strategy on a limit of finite dimensional strategies. So we could just start looking through finite dimensional strategies. And this is going to take forever. It's not really a practical process. But we would, in theory, converge to the right value from below. And on the other hand, for the commuting operator value, we also have a similar procedure. It's the NPA hierarchy. What that means is that we have a kind of infinite sequence of SDPs. And we can compute the value at each level. And if we do that, we'll get a sequence of values which will converge to this quantum commuting operator value from above. Both of them have the same limitation in theory. which is we have no way to tell how close we are to the right answer at any given point. So we might find that we've computed a value of 0.7 coming up to the tensor product value from below, and maybe we want to get within 0.01. Well, do we stop at 0.7, or do we really need to keep going and maybe we'll get up to 0.8 or 0.9 or something? There's no criterion to tell whether we've gone far enough, and the NPAA hierarchy has the same limitation. So once again, there's something finally we can say about this question, which is that it's undecidable to tell if the commuting operator value is strictly less than 1. So it's not quite the same thing as computing being able to say there's no algorithm which can compute the value to within any given precision. So it's not quite the same thing as totally answering the question, but it does tell us one natural task we'd like to answer about the commuting operator value is undecidable. And before I move on, I want to mention that the questions on the last slide, this question about computing the value, and kind of any other really basic, if you can't find the answer in the literature within 20 minutes, it's probable we don't know the answer to most of the kind of basic questions we can ask about non-local games. Okay, so let's talk a little bit about this. What does this mean? So it's not as good as saying it's undecidable to compute the value within some given precision. It does have some practical implications. Like if we think what it means for the NPAA hierarchy, imagine that what we'd really like with the NPAA hierarchy maybe is a function which would say, okay, for this game, if I want the exact value, then I just plug my game into this function. It gives me an integer k, and then I'm just going to compute the kth level of that hierarchy, and I'll get the exact value. So what this tells us is there's no such function. Any such function would have to be uncomputable. Now, it doesn't rule out the possibility that we could get a function which would say at the kth level you'll get within 0.01, or if you want to get within the within a millionth, you go to this level. We can't rule out that yet, unfortunately. This question is actually connected to the Tsirelson problem as well, the weak Tsirelson problem. If we did know that weak Tsirelson is true, we would know that the tensor product value and the commuting operator value are the same. So we'd actually have a procedure to do one from below and one from above. And since they're converging to the same value all the time, we'd know that we could just run these procedures until they were within the desired precision of each other and use that as our output. So this other question about whether we can actually compute to within some given precision would follow if weak Tsirelson is true. A lot of people think that weak Tsirelson is not true, although opinions vary and we really don't know the answer. So if weak Tsirelson is false, then we actually get no information about whether this quantum value is computable or not. One thing to ask is, well, when we talk about exact decision problems like this, just deciding if the value of a game is strictly less than 1, is that normally a decidable problem? Because maybe the undecidability is just hidden in the fact that we've used exact error. So one useful comparison point to think about is SDP programs, finite SDPs. Most of the algorithms you're probably familiar with use approximation. So you say, I want the value to within this desired precision, and hopefully, if no numerical instability arises or whatever in your actual computer, you get your output. But it's not the exact value. So it might seem like for SDPs, we would be out of luck if we want to decide whether within arbitrary precision the value is strictly less than 1. But the reason we mainly use approximation algorithms is because those algorithms are efficient. And if we're willing to look at inefficient algorithms, then there are algorithms to decide whether this is whether the value of an SDP is strictly less than 1. And there's probably more than one way to do this. I'm not an expert, but kind of if you really want to bring out the big guns, the real reason that's true is that first order logic for the field of real numbers is decidable. That means if you write down kind of any polynomials in real variables, put inequalities on them, and then put quantifiers on that and say, is this decidable? There's an algorithm for that. It doesn't run in any kind of a good time bounds, even for a lot of examples, small examples, but the algorithm does exist. And we can compare that to what we know for, it's a little surprising because if we compare that to first order logic for integers and rationals, that's usually undecidable. We actually get a pretty interesting kind of extension of this from the fact that the commuting operator value is undecidable. This was due to Tobias Fritz. I like this a lot, so I'm going to describe what he's done a little bit. So what he says is that imagine being quantum mechanics. What we'd really like to do, we don't care about numbers anymore. We really care about operators. So we want to do all our reasoning with operators in the place of numbers. So what we'd really be asking then is first order theory of projections on Hilbert spaces. And the kind of, there's a number, maybe you have to be an expert, which I'm not, to distinguish the different variants. But there are kind of a number of different ways to formalize this. They all kind of go under the umbrella of quantum logic. And what Tobias has showed is that quantum logic is undecidable. And it's, the undecidability part of it really follows from the fact that this problem for games is undecidable. So we can even make this really concrete just to kind of get a clear idea of what this means. So what kind of question would we ask? Well, let's say you want to know if there's a finite number of projections, P1 up to Pn, on some Hilbert space. You don't care about the Hilbert space dimension. It could even be infinite dimensional. But what you want is that certain subsets of them should be complete orthogonal projections. So you want, for certain subsets that you've picked out, the products of all the pairs in that to be 0 and the sum to be the identity. So what Tobias has shown is that this is an undecidable problem. And it's kind of it's very interesting that this is undecidable, because this is kind of what we do if we're doing stuff with quantum mechanics. We just write down projections and say, hey, are there projections like this? So kind of the basic problem here is really undecidable. And it tells us that if we're really replacing numbers with operators, then we're more trying to do things like, it's more like doing things over the integers than it is like doing things over the real numbers in terms of our first order theory. OK, so I've told you about two theorems. One is that the correlation sets for tensor-product infinite dimensional models and commuting operator models are different. And the other is it's undecidable to tell if the value of the game is strictly less than 1. These look like really different theorems. So what I want to tell you in the last part of the talk is that although these theorems look very different, they actually come out of one theorem, which is really a theorem in group theory. And so I don't want to talk too much about the group theory side of it, but I want to talk about how do we build a connection between non-local games and group theory. And it needs to be a really strong connection so that we can use all the different nice things that we know about groups and really translate them into things about non-local games. So the connection comes through something called linear system games. And a linear system game is very easy to describe. We start with a linear system, ax equals b over z2. And this is a game, so I need to tell you what inputs Alice and Bob receive, what outputs they have, and when they win. So the inputs are, we've got two players. We send one an equation, and we send the other player, say Bob, a variable. And what we really want to do is we want to check whether or not this system is satisfiable, whether it has a solution. So we're going to try and play Alice and Bob off of each other to see if they can prove to us that this thing does without having to solve the system ourselves. So what do Alice and Bob output? Well, Alice outputs an assignment to all the variables in her equation. That means that if a coefficient of a variable is 0, she doesn't have to output any value for that variable. Only the ones that actually appear with a non-zero coefficient. And Bob outputs an assignment for his variable. Okay, and they win in two cases. So one case is they get a free pass. That's if Bob gets a variable which is not in Alice's equation. So they don't have any overlap between the variables that they're outputting. And the other case is if there is an overlap, if Bob's variable does appear in Alice's equation, then the values that they output have to be consistent. So this scheme, even if you're not familiar with this notion, may seem familiar. It has a long history. Really, the first kind of example of this is the magic square game. So if you think about that, we've got some constraints on rows and columns summing up. So we get 6 equations there, one for each row and one for each column. And we get a variable for each kind of a square, so 9 variables. And so we can actually play that linear system as a linear system game. As a systematic class of games, I believe this concept is due to this paper of Cleve and Mattel, and it's also been studied by Jen Fang and Alex Arkhipov. Okay, so what do we know about this class of games? Well, the main thing to think about is what happens in the classical case. So in the classical case, it turns out that you can play this game perfectly, or Alice and Bob can play this game perfectly, if and only if the equation actually has a solution. So it really does seem to capture the right notion. But what happens in the quantum world? Well, if you think about the magic square game, we know there are these satisfying assignments, kind of contextual scenarios, where although the magic square game doesn't have a classical solution, there is this kind of quantum solution. And this carries over to linear system games more generally, that we can talk about a quantum solution, and there are cases where we have quantum solutions and no classical solutions. And a quantum solution, having a quantum solution is exactly the same thing as playing the game perfectly. So what do we mean by a quantum solution? Well, this is going to be something in terms of operators. It's convenient when working with observables to have plus and minus 1 eigenvalues rather than 0 and 1. So we want to write our linear equations multiplicatively. So we do that. That's our second line here. So this is just, we've just taken our linear system and written it in multiplicative notation. Our variables should be, let's say, Hermitian operators that square to the identity. So they have plus and minus 1 eigenvalues. And then we've got a third condition, which is really essential to the whole thing and really makes the whole thing kind of really be an interesting object. And that is, we want whoever is kind of using this as a solution has to be able to measure the values of all the variables in a single equation simultaneously. Which means that if we're thinking of these observables as being kind of quantum values of the variables, that they have to represent joint measurement for variables which are in the same equation. So if we have two observables which are in the same equation, so their coefficients are non-zero for the same I there, then those operators have to commute. And this theorem, which is the first part of which is due to Cleve and Mattel, says that we have a perfect strategy with tensor product models if and only if there's a finite dimensional quantum solution to this. In other words, Hermitian matrices that satisfy these three equations, three sets of equations. The second part of this theorem is joint work with Richard and Li Lu. And this says that we can actually extend this to the commuting operator case. And it answers the question of what happens if we allow infinite dimensional Hermitian operators here. There's no reason why we should exclude them. The definition makes sense if we allow the Hilbert space to be infinite dimensional. So what happens if we do that? Well, that's equivalent, having a quantum solution on a possibly infinite dimensional Hilbert space is equivalent to having a perfect strategy in commuting operator correlations. Okay. So where do we get the connection to group theory? Well, if you kind of think back to a group theory course, or I know some of you work very often with groups, one class of groups are those with a finite presentation. We write down some set of generators, and we write down some set of relations, and we look at the group that satisfies that. And we've got something close to that here. So we've got a bunch of symbols, xi, and we've got a bunch of relations they have to satisfy. The only problem is it's not quite a set of group relations because we've got this -1 right here. So how do we get around that? There's kind of a standard trick for it. We just make a new symbol that's going to be the -1. We call it j in this case. So it should behave like -1 if it's going to stand in place of -1. So it has to commute with everything. It has to square to the identity. And then we can just use that as a placeholder in our linear equations. And then we can just rewrite the theorem we had before in terms of this group that we get. So this group is called the solution group. So having a collection of matrices satisfying the relations of this group is the same thing as having a quantum solution. With one important point, we can't let the J be identity. So in a group representation is exactly that, a set of matrices that satisfy these relations. But if there's nothing there to say that J couldn't be the identity, so we have to explicitly exclude that. So what we get for the first part of this theorem is that the game has a perfect strategy in tensor product models if and only if the solution group has a finite dimensional representation. That's the same thing as saying before when we had finite dimensional quantum solution with J not equal to the identity. And we get exactly the same thing for the second part of the theorem with CQC, where we drop the finite dimensional part. And this is really obvious but really cool that we can actually drop talking about representations altogether at that point. Because if we're just saying, does this group have a representation where J is not equal to the identity? Well, every group has a representation where it acts on itself. If you've got an infinite group and you want it to be a Hilbert space, you can just close that up, do the standard tricks. And then you'll get that J is not equal to the identity operator in this representation if and only if it's not equal to the identity in the group. So what we get is we get kind of a simpler statement where it has a perfect strategy in CQC if and only if this element J is not equal to the identity. So everything about how we prove these two theorems that I've mentioned, you can see from thinking about this theorem, the direction that is. So what does it mean if we want to show that there's something in CQC but not in CQS? Well, we have to find a group which has a solution group where the J is not equal to the identity, but where it is equal to the identity in every finite dimensional representation. So if it's equal to the identity in every finite dimensional representation, then we'll have no perfect strategy in CQS. And how do we deal with the situation where we want to talk about decidability? Well, maybe you've already thought about this. What does it mean to test if an element is equal to the identity in a group? So we start with some finite set of generators. We write down some finite set of relations. And we ask, here's an element of this group. According to these relations, is it equal to the identity? Well, this is a really famous problem in group theory. This is the word problem. And it's known that it's undecidable. OK, great. From what I've just said, the undecidability theorem should come immediately, right? Yeah, not exactly. I mean, there are lots of we're talking about very specific instance of the word problem. So just because some instances, the whole family of groups, the problem is undecidable for that, doesn't mean that for solution groups the problem is going to be decidable. It might be that for solution groups the word problem is very easy. Most of the groups we work with actually have decidable word problems. Like if we think about the permutation group has a decidable word problem. Any finite group has a decidable word problem. And lots of infinite groups have decidable word problems as well. OK, so what we have to do is get around this problem. Rather than finding, saying, oh, well, the word problem is undecidable for groups, we need a way to show that the word problem is undecidable for solution groups specifically. So to get a little bit of an idea, is this something we would expect or not, we might try and figure, well, what makes solution groups special? And if you really think about it, the fact that we have, just to stare at these relations a little bit longer up here, the fact that we've got things that have to square to the identity as our generators, and the fact that we've got linear relations, that's all kind of incidental. The real key is this third part here where we say that if two things occur in the same relation, they have to commute. That's what makes this thing a quantum object. And it makes it very hard to find really non-trivial examples of solution groups. So think about this. You're allowed to write down a group with any relations you want. That can be really nasty. But whenever you write down a relation, you have to make everything in that relation commute. So let's look at an example of this. Here's a permutation group S3. It's generated by two involutions, A and B. And to get S3, we need a third relation, which is we say that AB cubed is equal to the identity. Those three relations are enough to give us S3. OK, what happened if we would make, so we've got A and B occurring in one relation there together. What if we made them commute because they occur in that relation? Well, AB cubed then would be the same as A cubed, B cubed, which would just be because they square to the identity the same as AB. So saying that AB is equal to the identity is the same thing when they're involutions as saying that A equals B. So what we really get instead of S3, if we had to enforce this local compatibility condition, is Z2. So it's a fun thing to do, to sit down and try and say, well, I'm going to try and make a group that's really complicated, so I get a really nasty solution group, but I have to obey this local compatibility condition. Can I do it? And the answer to this is that although solution groups satisfy this local compatibility, they can in general be as complicated, as general groups, which is actually quite counterintuitive. But we have any group at all, we can actually find an embedding of this group into a solution group. So it becomes a subgroup of a solution group. We can't guarantee that it is actually a solution group, but we can say it is a subgroup of a solution group. And more importantly, we can do that in a way that takes, if we have some central element, maybe I shouldn't say more importantly, but very importantly, we can do that in a way that if we have some central element which squares to the identity in our original group, we can make that be the j in our solution group. So we can really not just say that solution groups are complicated, but things involving the j are complicated. We can do a little more, actually. It's not on the screen here, but I'm going to get back to it on the last slide. We can actually guarantee that if we have any involution in our starting group, we can guarantee that it's one of the generators of our solution group. So we can actually do kind of embeddings that really allow us to see our original group to whatever kind of detail that we want, as long as we're talking about involutions. OK, so to finish, the last, well, actually, maybe, so I'm hoping you have questions. So maybe I'm not going to talk too much about how we prove this embedding theorem. There really wouldn't be enough time to say things anyway. But I will show you this picture. So what is in this picture? So I need to write down a linear system to do this embedding. And so how can I write down a linear system over Z2? Well, forget about the B for a second. Just concentrate on the matrix A. That's an m by n matrix with entries in 0, 1. So I can, this is very fortunate because if we're talking about complicated linear systems, it's really hard to write them down any other way. We can write them down graphically, thinking about the columns as edges and the rows as vertices. We're just talking about hypergraphs. So here's the hypergraph for the group written at the bottom. Actually, if you really follow through the embedding that you want to do for general groups, this is already not complicated enough. You need to do some pre-processing. But for this specific group, this is good enough. And the key idea is in there. So you would translate this. We look at this one relation, x, y, x, z equals the identity. So for every relation like that, you translate them into one of these wagon wheel shapes. So you make the hypergraph where on the outgoing kind of, maybe if this was actually a wheel, you'd put kind of some big spikes here. That's where you put your original variables. And then you have a bunch of auxiliary variables kind of forming this wagon wheel shape. So if we think about this as a game, basically we'd be sending Alice a vertex and Bob an edge here. And they'd play the game where they have to output an assignment where Alice's product around, she has to output an assignment for every edge around here. They win if it agrees with Bob's assignment, or if there's no overlap. And Alice's assignment has to always be, the sum of the 3 variables has to be equal to 0. OK, so one last thing. So I want to talk about this third thing here. And there's a lot of further directions we could go with this. The kind of embedding theorem we have now is still pretty rough, and I think could be improved in a lot of ways, maybe leading to some interesting applications. And one of them is, that I think is maybe the most interesting, is what can we do with the fact that we can embed an arbitrary group inside a solution group. That really means we can force Alice and Bob, if they want to play this game optimally, to apply operations from any specific group that we want. The caveat with the embedding theorem we have now is they might then need to actually implement this infinite dimensional Hilbert spaces. So we really, to make this practical, need a version that would allow us to start with things that have finite dimensional representations and turn it into something that has finite dimensional representations. Maybe we can't do that for all groups, but we might be able to do it for specific groups or specific classes of groups. And this would have some really interesting applications, I think, for things like self-testing and device-independent protocols. So with that, I will stop there. So thank you.
Questions?
Does it make any difference whether in the infinite dimensional case the Hilbert space is separable or not?
No, it doesn't actually. Because your algebras are always finitely generated, actually. You can make like you really only care about the So you care about the state, your entangled state, and then you care about what the operators do to that state. And because you really only have finitely many operators, you can always reduce it to separable Hilbert spaces. So although we, in commuting operator world, we do need infinite dimensional Hilbert spaces, they don't need to be very big.
Sorry, I might have missed this, but did you already say that CQ and CQS are not closed?
We don't know if they're closed.
We don't know if they're closed.
Yeah, CQ and CQS, we do not know if they're closed. Yeah,
Okay.
It's possible. All we know is that CQS is not equal to CQC. But it's possible the three tensor product ones are all equal. Yeah.
Okay. More questions? Well, let's thank the speaker again.